Let's look at solving systems of linear equations by elimination. So ideally, we want our equations to be in standard form where we have additive inverses. That's the perfect setup to solve by elimination. Well, what are additive inverses? Additive inverses are the same term, different signs. Therefore, when added together, they simplify to zero. And that allows us to eliminate a variable. Therefore, we're working with just a one variable equation so we can begin the solving process. So looking at this system, do we see additive inverses? Well, yeah, x and negative x, all right? So that means when we add our two equations together, remember we combine like terms, so we have x plus negative x is 0, 2y plus negative 4y is negative 2y, and then 4 plus negative 14 gives us negative 10. Notice those additive inverses simplify to 0, so now we're left with a one variable equation. So we just solve for y. So we divide both sides by negative 2, and we get y equals 5. So already we have half of our solution. And so now we take that 5 and we substitute it back into either the first equation for y or the second equation for y. So it doesn't matter which one. I'm going to pick that first one just because I see smaller values. So I have x plus 2 times 5 equals 4. And we just begin the process for solving for x. So we have x plus 10 equals 4. And now we have x equals negative 6. So our solution here is negative 6, 5. Remember, we can check that. To check it, we would substitute the variables back in. They should make both equations true. So negative 6 plus 2 times 5 equals 4. We would get 4 equals 4. And then negative 6 minus 4 times 5 equals negative 14. And we get negative 14 equals negative 14. Because remember, the solution to a system is the ordered pair that those equations have in common, or the ordered pair that makes both equations true. Okay, let's pause the video and try this one on your own. Okay, looking at this system, we're looking for additive inverses. Okay, so we have 5x and negative 5x. It's the same term, different signs, so when we add our equations, 5x plus negative 5x simplifies to 0. Negative 6y plus 4y gives us negative 2y. And 6 plus negative 14 gives us negative 8. Then we divide both sides by negative 2 to get y equals 4. And now we take that 4 and we substitute it into either the first equation for y or the second equation for y. Does not matter which one. You could have picked either one. You should still get the same x coordinate. So we begin the solving process for x. And we get x equals 6. Therefore, our solution is 6, 4. Okay. Try this next one on your own. All right, let's look. Do we have any additive inverses? Okay, so you probably either noticed negative 2x and 2x, or maybe you noticed negative 4y and 4y. Maybe you even noticed both and you were a little confused. So when we add here, we get negative 2x plus 2x is 0. Negative 4y plus 4y is 0. So our left-hand side, we have 0 equals. And then 10 plus negative 10 is also 0. Okay, when we get 0 equals 0, what happened? If you're thinking our solution set is infinitely many solutions, you are exactly right. Because remember, whenever you're solving a system algebraically and you get down to a point where there is a true statement, right? 0 does equal 0. Then you have infinitely many solutions, because that means our two lines have the same slope, same y-intercept. They're the same line. So they have infinitely many intersection points, therefore infinitely many solutions. Now, if you ever get to a false statement, then that would be no solution. But here, 0 equals 0 is true. Therefore, our solution set is infinitely many solutions. Okay, let's look at one more. Try this one. Okay, so we are going to look for additive inverses. We have 2y and negative 2y. So that means we can go ahead and add our equations. So we have 2x plus 6x to give us 8x. 2y plus negative 2y gives us 0. We have negative 4 plus 12 to give us 8. Divide both sides by 8 to get 1. And then we take that 1 and we substitute it back into either the first equation for x or the second equation. Does not matter which one. I'll just pick the first one. So x is replaced with 1, and now we are solving for y. Subtract 2 from both sides. And so y is negative 3. So our solution here is 1, negative 3. Okay, so for all 4 of these, we found additive inverses and then began the elimination process. Sometimes you'll have a system that you would have to create additive inverses before you can begin the elimination process. That's always going to be the very first thing you look for. Does our system have additive inverses?